Hello, and welcome to the Chemistry Show. Today I will be introducing and showing two gas laws. One being the ideal gas law, the second being Charles' law. For our ideal gas law experiment, we will be using a balloon, compressed air, and a hairdryer. Our experiment will consist of blowing up the balloon to an average size, taking the volume and measurements of this balloon, then heating the balloon up with the hairdryer, taking the volume of the balloon while it is heated up, and then cooling the balloon down with compressed air. All these results will have a different measurement for each one. We will be taking these measurements and using them to prove our ideal gas law. First, we will be doing an experiment for our ideal gas law. The ideal gas law has an equation of PV equals nRT. P meaning pressure, V meaning volume, N meaning moles, R the constant, T meaning temperature. Today, we will be using an experiment that proves temperature affects volume. So, for this experiment of our ideal gas law, we'll be using our balloon, our hairdryer, our compressed air, a string to measure the volume of the balloon. We will be using the string to measure the circumference, which we will later use to find the volume. We will be using safety gloves just in case for the compressed air. And then I have my tools for taking our measurements, which we will then use later to prove our gas law. So, we have our balloon just blown up, about average size, and I will take our piece of string, put it around our balloon to find our volume, and I will mark it. Okay, then we'll take a meter stick. Unfortunately, I do not have one that is in centimeters, so I'll have to find it in inches and then convert to centimeters. So we have 26.5 inches. So 26.5 inches times 2.54 equals 67.31 centimeters. So our initial volume of our standard balloon is 67.31 centimeters. Now, if I take a hairdryer and I heat this balloon up, the balloon should get larger because the temperature is increasing, so the volume of the balloon will also increase. As you can see, it's getting a little bit larger. Okay, now we need to take a quick measurement before it returns back to its normal size. Wow, I almost can't even get the string around it. Get our measurement. Okay, I've got the marker, so the balloon should be good to go now. Let's get this measurement. Wow, 27.5 inches. So we have 27.5 inches. Let's put that into, let's convert that. 27.5 times 2.54, 69.85 centimeters. So, that was good. Worked very, very well. So, now, we will be taking our compressed air. The compressed air is somewhat dangerous, so I will be putting on protective gloves if it touches my bare skin, which I'm not planning on it. So, actually I'm going to take this off to assemble it. One moment to break the seal. There we go. Okay. Compressed air is ready. So, the compressed air should make the balloon smaller than its original volume. Here we go. It is definitely getting smaller. Wow, that's a lot smaller. All right, that should be good. Let's take our new volume. Okay. A lot of room. So I'm gonna put our balloon down here. Have all three of our measurements. Oh my goodness, 24.5 inches. It's a significant difference. Okay, 24.5 times 2.54, 62.23 centimeters. So, there you have it. Our first experiment for our ideal gas law worked very well. Now for our second experiment. This is a good one. We will be using two different sized soda cans. One being 221 milliliters. The second being 355 milliliters. We will also be using heat to aid in this experiment. For this experiment, we will be trying to prove Charles' gas law. P1 over T1 equals P2 over T2. Pressure over temperature equals the same. The pressure inside will change drastically because of the temperature. For our second experiment, we will be using the two cans that I showed earlier, with the small can being 221 milliliters, the large can being 355 milliliters. What we'll be doing is we will be pouring about a ½ ounce of water into these cans. Then we will put them on a stovetop to heat them up. When they heat up, the water inside these cans will start to boil and it will become water vapor. Then I will use tongs, take the can, place it upside down in a cold bowl of water. When the warm vapor inside the can hits the cold vapor inside the bowl, the pressure will increase so much that the can will crush immediately. Wow.
Avoid any distractions. One day this
Wow. That one might Okay, these are our calculations for our balloon experiment. We're using the formula V1 over T1 equals V2 over T2. We start with our initial volume and temperature of our balloon from our room temperature normal average size balloon. We started with 67.31 centimeters. We divide that by 100 to get meters, which is 0.6731 meters. Divide that by 2 to get our radius. Now we have 0.3365 meters as our radius. Now we're going to plug this radius into the formula to find the volume of a sphere, or our balloon. So we have 4/3 pi r squared. I'm going to leave it in terms of pi. 4/3 times pi times 0.33655 squared gets you 0.151 pi. So that is where our volume 1 comes from. The temperature was 344 degrees because of, oh, I'm sorry, this is the hair dryer, because of the hair dryer. And then with our room temperature balloon, which was 0.163, we get that from the original 69.85 centimeters. Divide that by 100, get 0.6985, divide that by 2, which gives you the radius, which is 0.35. So now we have the volume of the second one. And now we are going to the temperature of that one, 295 degrees Kelvin. Now we divide it up. We had 4.39 e to the negative fourth equals 5.53 e to the negative fourth. A very close comparison. So this proves our experiment with the balloon. Okay, now for our can experiment. For our can experiment, we are going to be using the same formula. V1 over T1 equals V2 over T2. So I'm going to use the starting volume and temperature of our can, which was 221 milliliters over 295 degrees Kelvin. Okay, that was our starting. After it had crushed and came out, we were met with 95 milliliters over the temperature when it crushed, 373 degrees Kelvin. Okay, now let's work it out and see what we get. We get 221 divided by 295. 0.75 equals 95 divided by 373 equals 0.25. Again, they are not exact, but they are similar enough to where it works. So now we have proved Charles' law again in our can experiments.